Okay? And of course, if you have questions at any point, please ask me, all right? So, transformer design project. First thing that we have to do, and this is probably obvious, is to choose a specification. In other words, what type of transformer do we want to build? Okay? So I'm going to call this one step 0, because step 1 in the handout refers to something else. So this one is step 0, okay, is to choose a specification. In other words, we want to know what is the rated voltage, okay, and rated kVA values, okay. The numbers I'm going to choose here, okay, these are for this example, okay? When you do it, I want to make sure that you choose your own numbers, okay? You can vary certain things. So for example, I'm going to choose 100 kVA transformer. You could make it 175, or you could just make it 75 kVA if you want. Whatever you want, okay? And you could play with the voltages. Now, this is something we haven't talked about yet because it sort of relates to power electronics. So let me introduce it and then I'll talk more about it. So make sure it can handle up to the 9th harmonic. Okay? Up to the 9th harmonic. I have to explain, obviously. I have explaining to do. Okay. So, a harmonic, I think the easiest way to understand harmonics is to think of, for example, 2 different musical instruments. Okay? If you take a piano and a guitar and you play the same note, let's say on the piano you play 440 hertz. You play A. This is the note A, by the way, on the piano. And you play the same note on the guitar, right? It's going to be the same note, but you're going to know, like, that's a piano, that's a guitar, because it sounds a little bit different. So the 440 hertz, which is the note A, okay, is going to be the same for both the piano and the guitar. That's called a fundamental frequency. Okay? That's, you can think of it as the first harmonic. Now, what makes the guitar different from the piano is that the guitar has different harmonics that are being basically sounded when you pluck the string than a piano has. That's what makes them sound different. Okay? Is that they have different harmonics. And harmonics, when it comes to electrical engineering, these come about really from power electronics. So for example, AC to DC converters, AC to AC inverters, all these different devices, basically, they tend to distort the signal of the voltage or the current. So for example, we've been dealing a lot with sine waves like this, a nice sine wave, right? Sine waves are a very pure signal. That's a fundamental frequency. But what if we had, for example, a square wave, right? A square wave has harmonics. It has a fundamental frequency that you can identify, but it also has some additional harmonics involved in it. So basically, if you were to add these harmonics, you get the square wave. If you just take out the fundamental frequency, you get a sine wave. Okay? Have you guys talked about this in series, Taylor series, Fourier series? None of that sounds like gibberish, right? Okay, so in short, I have a little demo. Hopefully it'll work. I have GarageBand here. Okay. So, for example, let's see if it plays. Okay, it plays through there. So, for example, this note that I'm playing, right, this is an A. Okay, that's a piano. All right. Now, if I were to change it, I could, for example, change to an electric piano. it's the same note, but it sounds a little bit different, right? The tone is different. Like this, it kind of sounds like computerized, like a little bit kind of, in a way, it sounds very pure, right? Whereas if you were to go here, it sounds different, okay? And if you want to, like, let's say we can do like a synthesizer, same note, but it sounds kind of weird, right? A little bit different. So basically all of these instruments have what's called different harmonics, okay? And you could change whatever you want. If you have GarageBand, you could play with this. For example, I know because I've worked with music before. I'm trying to see if they have a square wave. The square wave is going to sound a little bit distorted. Let me see if I have here something to show you. For example, if you were to take a guitar and just turn the electric guitar and turn the volume up really high, and do like a, something like this, right? That type of sound, okay, is more like a square wave, okay? Whereas if you were to go and do something like this, it's more pure. This is more like a sine wave, okay? Anyway, if we have time later, maybe we can make beats on GarageBand. Okay, let me just get rid of this. All right. So we need the transformer to be able to handle up to the 9th harmonic. A couple other things that I would like to mention is make sure, okay, the efficiency has to be greater than 99%. What I mean by that is 99.1, 99.01. Even if it's a smidgen above 99%, you're good, okay? And you're going to test the efficiency at power factor equal to 1, unity power factor, okay? Okay. So, let's start with the example that I have here. So, example. The transformer that I'm going to build is a 100 kVA, okay, 6600 volt to 600 volt, 60 hertz transformer. All right. So, of course, you can change these numbers. All right. For example, maybe if you want to leave it 100 kVA, great. Then you could change this. Maybe make it 480 to 240. Play around with it. See what you get. Okay. This is your time to be creative. Okay. Now, we have to consider the 9th harmonic. Okay. So, let's write this. 9th harmonic requirement. Okay. Basically, the highest, what the requirement is that the highest frequency that can run through the transformer is the 9th harmonic, okay? Which I'm going to show as F subscript 9, okay? And it turns out that harmonics are integer multiples of the fundamental frequency. So for example, your fundamental frequency, I'm going to call that F1. Okay, that's your fundamental frequency. The 9th harmonic is going to be 9 times F1. Okay, so it's an integer multiple of the fundamental frequency. All right. by the way, in our speaking voices, we also have harmonics in our speaking voices. That's why one person's voice sounds different from the other. Okay, if you were to sing, let's say, the same pitch, it would sound different, right? Because you have a different voice. Okay. So, our fundamental frequency is going to be 60 hertz. We live in North America, so it's 60 hertz. And we can find now the frequency of the ninth harmonic. It's going to be 540 hertz. Okay? And this is going to be important in our design process because our transformer needs to be able to handle that. All right? Okay. So, let's now go to step one. Step one is from the specs that we decided on, okay, calculate I rated on the high side and I rated on the low side. Okay? This is almost like a homework problem, this part. Standard stuff, nothing too crazy. So how can we find, for example, I rated on the high side? What do we think?
Can you start with the voltage on the high side?
You're going to need the voltage on the high side for sure. You need that, right? But you need one more thing. Voltage and something else to find I rated. The what?
The base?
Not the base. We're not looking at per unit this time. Okay, we just want what is the rated current, what it should be on the high side.
You need the resistance.
No resistance. There's another number we can use to find it. Maybe, well, if I add what I'm going to add, I'm going to give it away.
P equals I squared R.
You have the right idea. It has to do with power, but not that equation. You have the right idea, though. Slightly, not that the equation is wrong, it's just we don't have a resistance to work with. Okay. Right. S. Okay. This is, maybe I should have added there, S rated, right, is the 100 kVA. So I rated is just going to be your S rated divided by V high side rated. Okay. The equation I was looking for, by the way, was S equals VI. Okay. Just to keep in mind. So S, we have here 100 kVA, so times 10 to the 3, volt ampere, divided by VHS, which is 6,600 volts. And when you punch the numbers in, you're going to get 15.15 amps. All right? You can do identical, same thing on the other side. I rated low side is going to be S, but now you're going to do V low side. Okay, so S is going to be, again, 100 kVA. Voltage on the low side is 600 volts. And you're going to end up with 166.67 amps. Okay. Those are the rated currents. But what we're going to do, okay, we're going to over-design it. What do I mean by that? Well, there's several things that in life are for sure. Death, taxes, short-circuit currents in power systems, okay? Overcurrents. In other words, if you connect this thing to the power system, there's a very high likelihood of chance that you're going to have a very high current that exceeds the rated. Okay? It's going to happen. The other one is that the internet here is going to crash. This happens at least once a try. It's happened. I think it happened today. I don't have internet. I don't know about you guys. Okay? Blackboard is another one. Is Blackboard's going to crash. Okay? And of course, we have the overcurrents in our electronic equipment. So what we're going to do to basically protect ourselves from that is we're going to add or increase the rated current by 15%. Okay, so that's step 2. We increase rated current by 15% safety margin. Okay, so this is a safety margin. So basically, say it again.
And this would be to prevent overcurrent or just counteract it?
It's basically, we're designing the transformer to handle 15% over what we say it can handle. Okay? Let me explain. So on the nameplate, you're going to see this. Okay? So the whoever buys our transformer is going to hook it up and they're going to say, okay, this is the nameplate data. It can handle, based on calculations, these are the rated currents. However, they don't know, but we designed a transformer to handle 15% over these values. So just in case something goes wrong, the transformer is not going to get damaged. It'll be able to handle a little bit more than this. Okay? That's basically the idea. Okay? For example, when you're driving the car and the fuel indicator goes, the empty light turns on, you still got gas in there. It's not totally empty, right? You have a little bit left, right? But, the car is designed to have enough gas that when it says empty that you can make it to the gas station and fill up. Okay? A similar concept to this. All right? So, let's do it. So I high side, okay? Basically, we have to multiply the rated value by 1.15 because we want to increase by 15%. So it's going to be 1.15 times 15.15, okay? And that's going to turn out to be 17.42 amps. And we do the same business with the low side current. Whoops. And this is going to be 191.67 amps. Okay. So now when we decide what type of cable we're going to use, okay, we're going to choose a cable that can handle these values of current, the high current. In other words, the 15% over. Okay. I have a little power cable I'm going to pass around later, so I'll just put it here. Okay. So, then basically, this is still part of step 2, is we're going to select the cross-sectional area using the rule of thumb. I'll explain it, don't worry. Okay. Rule of thumb is 1,000 circular mil per amp. Okay. So, essentially, the circular mill, by the way, in case you guys forgot, this was discussed in Intro to Electrical Engineering, which was a long time ago. Okay. Long story short, circular mill is basically like the cross-sectional area of your cable, basically. So, for example, this one, the cross-sectional or the circular mill, they actually write it here in AWG. So if we go here to the, I have the table here. The cable I'm holding in my hand is basically this thick. Okay? So the circular mill is this. Basically, it's telling you the cross-sectional area of this cable. Okay? Let me go back. So we're going to find how big the cable has to be from this rule of thumb. So by the way, let me see how I did it with the other section so that I want to make sure that I do it the same way. Okay, so let's do it like that. So we select, or rather, let me check one more time. Okay. So, just to review, one circular mill. Anyone remember what one circular mill was? Okay, we'll review. A circular mill is the area of a circle with diameter equal to, or I should say, with a diameter of 1 mil, where 1 mil is 1/1000th of an inch. Okay, in case you forgot, this is just a review. You don't need this for the transformer. It's just to remind you what a circular mill is, so you know I'm just not making up stuff. Okay, I put it in the blue box. This is review. Okay. We're going to be, in our example, working with circular conductors like this. Okay. This cable, for example, I wouldn't put this on a transformer. It's pretty thick. But if it was a very big transformer and it was required, then we'd have to find a way to do it. But anyway, the idea is, okay, we're going to be dealing with circular conductors. And because of that, this is another helpful formula to have. The area in circular mill for a circular conductor, if I have the diameter in inches, this is how I find the area in circular mill of a conductor. This is also review. Okay, this is just for your own knowledge. You may need it later. Okay. All right, so that was just sort of an aside so that you have in your notes this. Let's actually calculate now the area in circular mill for the high side. So let me do it like this. Back to rule of thumb. All right. So the area in circular mill for the high side, right? We use the rule of thumb, which is 1,000 circular mill per amp. And we multiply by the current that has been jacked up by 15%. Okay? So the current that we had for the high side was 17.42. And when you calculate this, you're going to get 17,420 circular mil. So basically, the conductor on the high side should have a circular mill area of 17,428. Okay? And we determined that by using the rule of thumb and the current that's 15% higher than the rated. So notice, my conductor is going to be a little bit bigger because I want it to handle 15% more than it should, basically. So questions so far on this? I want to make sure everyone's following. If you're lost, please tell me. Okay, so we can use this formula now to find out what does the diameter of my conductor have to be in inches. So for example, my diameter in inches, right, if I were to basically solve for d in, okay, it's going to be the area in circular mill over 10 to the 6, everything under the square root. So basically, if I want to find d in for my high side conductor, right, in inches, I take my circular mill, divide by 10 to the 6, and then take the square root, and I'm going to find that the diameter in inches should be 0.132 inches. Okay? Let me give you a moment to write that down, and let me reiterate what we're doing, okay? So, this is the size of conductor that I need to be able to handle that current. Okay? This is basically the cross-sectional area of this conductor that I need. Now, if I want to find the actual diameter, right, the diameter of this conductor, the circular mill is a cross-sectional area. I want to know what the diameter is. I can use the formula from review to find the actual diameter in inches if I want to. Okay? It's good to have that information written down. Okay. How are we doing? Good? Not good? Okay, good. All right. Let's do the same thing for the low side. Again, we use rule of thumb. And the low side current is supposed to be 191.67 amps. So when we punch the numbers, we're going to get that the circular mill area that we need is 191,670 circular mill. And if you were to find the diameter, and maybe I should do it like this, excuse me, diameter in inches for low side, okay, you would do the same formula, right? And you would arrive to the answer that this diameter must be 0.438 inches. Okay? So basically, if you want to highlight some numbers, this is a good number to highlight, and this one as well. Okay. So we're going to do now, we're going to go to the table. I'm going to give you this table. Okay, this is from the Intro to Electrical Engineering. This is it. Okay. And we're going to find the cable that we can use. Okay. So you'll notice, I don't know if you guys remember this, you have several ways to measure it. You have the diameter of each wire, all sorts of stuff. Here we have something called AWG. So my mentor from the PhD program used to call AWG North American Madness. Okay. Why? The thinnest cable is AWG 18. As I increase the size of the cable, AWG starts to decrease, right? So basically, AWG 8 is a fatter cable than AWG 18. And then all of a sudden, we start going to 0, double 0, triple 0, quadruple 0. And once they got tired of the zeros, now they go back to numbers, okay? The only explanation for this, of course, is job security, to confuse the mechanical engineers so that they don't know what this means, okay? That's why. It's the only reason why, okay? It's confusing even sometimes myself when I look at this chart. I'm thinking, oh, 18, that's a big cable. And I realize, oh, wait, it's not, right? So it can be very confusing. This is why circular mills are easier to work with, okay? Now, so for now, just sort of ignore this, the AWG column. I don't want you to get confused. We're going to really be looking at this column. Another column I want you to look at is this one. Number of wires. Okay? Notice that the smaller cables are all solid. In other words, you have a solid piece of copper. Okay? Solid piece of copper. But once the cables start getting a little bigger, you start to see now 7 wires, 19 wires, 37 wires. Okay? And if you look at this cable, for example, this one also has, I haven't counted them, but they're stranded. Okay, I'll pass that around so that you can see. So in other words, instead of having a solid piece of copper, you actually have individual smaller cables, stranded. Okay, and I'll pass it around so you guys can see the part here. Okay. That's actually one of the power cables I use in my experiment. Okay. So, anyone know why they're stranded? Why all of a sudden we start stranding?
Skin effect.
Say it again? Skin effect. Right. It's because of the skin effect. Okay, we're going to talk about it in just a moment. The skin effect is why we have to strand it. All right? And the skin effect is also why we have to consider the ninth harmonic, because the skin effect is affected by the frequency. Okay? Be careful not to get scratched on the, it has like a little shielding, not to scratch your finger on it. Okay? So, let's talk about skin effect. Let's talk about it here. Okay, so skin effect. Imagine that we have a solid conductor like this, very thick, just one big solid piece of copper, let's say. Okay. And let's say that we're running some AC current through it. So half the cycle is going to increase coming out of the page, and then the other half of the cycle is going to do the opposite. Okay, so it's going to go back and forth. Let's assume that we're observing this conductor when the current is increasing out of the page. Like this. Okay? Current is coming out of the page. Because this is a solid piece of copper, okay, this increasing current is going to basically cause eddy currents to form. Let's see how that happens. So first of all, if I have current coming out of the page, I'm going to have a magnetic field that goes counterclockwise, right? By right-hand rule. You point your thumb in the direction of the current, your fingers will curl in the direction of the magnetic field. Now, this magnetic field is not only going to be outside the cable, it's going to also be inside the cable, right? So this, basically, if you look at this current here, you're going to have like this magnetic fields everywhere, right? And they'll all add up eventually to the whole big one. So let's consider the, I did it a different direction. Whoops, like this. Okay? And as the current is increasing out of the page, that blue magnetic field will also be increasing. Okay? And let's consider, for example, let's consider a loop of wire, or rather just a loop like this, okay, inside the conductor. In other words, if you were to consider, let's say this is the conductor. If we consider just a piece of metal, in other words, a piece of the conductor, you can imagine inside, right, like a loop, basically. It's a solid piece of copper, so you can think of it as an infinite number of loops anyway, right? So you have a little loop in there, and what's going to happen is that this magnetic field, right, is increasing through the loop. So what's going to happen in this gray loop? If the magnetic field is increasing through the loop like this. Imagine this is a solid loop. I did it dashed here to show that it's like inside. Okay.
Is it also increasing?
In which direction? Yes. So in other words, as this magnetic field tries to increase through the loop, there will be a current that forms in the loop such that it has a magnetic field to oppose the blue one. Okay? So the effect is that the eddy, basically this gray arrow is showing an eddy current, where the eddy current basically is going into the page here, and on the other side is coming out. And that is going to happen at every single point. Okay, if you want, I could just copy it and show you. It's going to happen everywhere. It's going to happen here. Okay. It's going to happen here. All right. Everywhere, really. Let's not crowd up the picture, though. So overall, what this does is it basically, notice what happens. This guy is going into the page. This guy is coming out of the page. So they cancel out. Okay? And the overall effect is you are basically going to cancel out all the current in the center of the conductor. All right, so basically what's going to happen, I'm going to do it in green. This gets canceled out, this gets canceled out, this gets canceled, this gets canceled, this gets canceled, so on and so forth. The current that will survive will be the one in a small ring on the outskirts of the cable. Basically what's happening is that in the center of the cable, the current is being canceled out. If you were to just drill out that center and just put like a pipe, it would run just fine. Okay, it's the same thing, essentially, because it cancels it out in the center. We don't want that though, right? If we want a size conductor like this, we want it to be able to basically send as much current as possible. Okay? So this thickness right here, this thickness, all right, through which current will actually flow is called the skin depth. Okay, like a layer of skin, basically. All right? That's the skin depth. And depending on the frequency of the current and all sorts of other things, right, that can be thicker or thinner. Okay? This only happens with AC current. Okay? DC, this doesn't happen. Only AC, because you have this changing current and changing magnetic field. Okay? Okay. So, let's put here a note. Here, note on harmonics. Because the harmonics are going to affect this. Basically, this happens due to the frequency of the current. So, when you run an AC current through a conductor, okay, you get the skin effect. All right? Now, what if, instead of making this just one big solid piece of copper like this, what if I made the conductor to be exactly this diameter? If I were to do that, there would be no skin effect because it's too small, right? It wouldn't be able to cancel out stuff in the middle because it's exactly the size of the skin depth. Okay? So instead of making this one solid piece of conductor, I could make it stranded out of cables this small, and the skin effect will not affect it. Okay? Of course, these strands would have to be coated with some sort of enamel so that you don't necessarily have short circuits and stuff like that, right? But essentially, I can still push the same current that I would want through this whole thing, but now through strands. Okay? That's the point. That's basically what we're going to do. So we have to find what is the skin depth at the 9th harmonic so that we have enough strands and also that the strands are basically small enough that we don't have skin effect. Okay, so let's just on the next page. Delta, which is your skin depth, is proportional to 1 over the square root, and I should put proportional, not equal. It's proportional to 1 over the square root of the frequency. So, for the fundamental frequency, let's call that delta 1. Okay, we have, of course, this relationship. Now, we have a similar relationship, or basically the same thing, for the 9th harmonic. Okay, and by the way, for copper, the skin depth is going to be 0.37 inches. Okay? It turns out to be that way for copper at 60 hertz. Okay? So from there, we can find what is delta at the 9th harmonic. Okay, we can basically just take the ratio of the two, so I get delta 1 over delta 9, and I'm going to get the following. I'm going to have on top 1 over square root f1, 1 over square root f9, okay? Let's put it like this. So I have 1 over f1 is going to be 60 hertz. And f9 is going to be what we calculated before, which was 9 times 60 hertz, so 540 hertz. Okay. If I plug in, right, delta 1 equals 0.37 inches, I can solve for D9, or delta 9, right? It's going to turn out that delta 9, okay, is going to be 0.123 inches. Okay. So basically, we want each individual, if you have the cable, right? Each individual strand in there, have you seen it? Each individual strand, for our case, must be less, basically the diameter must be either this value or less, not greater. If it's greater than this, you're going to have skin effect. It has to be less than this. Okay, I'll write that down. So diameter of each individual strand must be less than or equal to delta 9. Okay? Okay. This class ends at 3:35, right? So, I just want to add one more thing before we finish up. Tomorrow, there's that barbecue, so we're going to be shifted, I think, right? Our class is going to be 7th and 8th period. Do you guys normally have 6th period free? Right. In other words, do you normally have 5th period free?
We moved it. We're having it earlier in the day.
Oh, so you would tomorrow have 5th period free?
Yes.
So we could meet our normally scheduled time at 2:40. Okay, so we can do that, and I have to talk to Professor Kelly.
Would it just be 5th and 6th tomorrow?
It would be 5th and 6th tomorrow, right? But it's as if it's 6th and 7th because everything is shifted.
Okay.
You understand?
Yeah, I understand.
So let's meet again, 2:40 tomorrow. Okay, we'll have to pick up with this tomorrow. We'll have the quiz tomorrow. Okay, so basically, let me just finish this, just one comment here, and then we'll finish. I want to end on a high. Let's end on something good. Okay, so basically, we're ready now to pick our conductors. Now, I did this ahead of time. I highlighted it for you, but let's just remember, okay, we need, for the high side conductor, has to be 1740 or 17420 circular mil, the thickness, right? 17420. So let's go back here. Okay. We have 16510, but we don't have 17420, right? So we just choose the next highest one. Okay? We choose the next highest one. This one is stranded with 7 wires, and we look at the diameter of each individual wire. See, diameter of each wire, okay, is given here. And we were supposed to be equal to or less than 0.123, right? The other one was 0.067, so it's smaller. We're good. Okay? We do the same thing for this guy. This guy's supposed to be 191,670 circular mil. So we look for 191. We don't have it, so we go to the next higher one. Okay? This is going to be 19 strands, and we see here the diameter of each individual strand is 0.1055, which is still less than 0.123, so we're fine. Okay, so these are going to be the conductors that we're going to choose for our example. We'll finish this tomorrow. Okay, so we'll meet normal time tomorrow. Say it again?
Said 4-aught wire, that's thick.
That's thick, yes. Believe it or not, you could do it. Okay? But it is thick.
4-aught all the way to 6-aught. That's crazy when it translates. Are we going, or is Friday the 3rd is a Monday schedule, and I'll be going home that weekend?
Friday the 3rd.
Yeah, Friday the 3rd.
Okay.
You can sign off.
No problem.
I already got mine.
Where do I sign again?
Electric machines.
I see. So I approve you?
Yeah, approving.
I approve, and then I sign. That's not the end of the term, is it?
Oh, no, it's not.
It's
Sir, two of us we're in a different
Thank
section,
you.
so we have a class.
You mean tomorrow?
During fifth.
Okay.
Like, we can just have someone send us the notes if you're moving class.
No, you should be here. So tell them, okay, that we're gonna meet instead during, normal 6 and 7.
6 and 7. Okay.
Right. Tell them that we have to do that because I don't want you guys to miss this.
Okay.
All right. Oh, what's his name? Forgot the pen. And we're live. Okay. So we were talking about the skin effect yesterday, and we were talking about how we have to account for the skin effect, and we wanted to account up to the 9th harmonic. So, long story short, it turned out that for the 9th harmonic, the thickness, the skin depth, was 0.123 inches. Okay? So basically the strands in our conductor have to be equal to 0.123 inches or less. It cannot be more, okay? So this is something that we'll have to consider when we're looking for what type of cable we actually want to use. So we have here, right, from the rule of thumb, okay, we found basically the size of conductor that we would need, okay? And we looked at the skin effect to figure out what size of strand we would need, okay? So basically what we're going to have to do is we're going to have to look at the table, which I've given you, the AWG table, and we have to basically locate which would be the best. In other words, we want something with a circular mill area ideally equal to this, okay? But if we can't have it exactly equal, we want it a little bit larger. We don't want to err on the side of being too small, okay? So for the high side, right, we want circular mill area of 17,420 or 17,420 circular mill. So we go to our table, which is over here, okay, so 17,420, and we see that we have here 16,510, and the next highest one is a little bit higher than what we're looking for. So it's okay to be a little bit higher. We're going to actually select that one, okay? Now, this one is stranded, and we have to just double check that our stranding, right, matches the requirement for the ninth harmonic. The ninth harmonic was supposed to be 0.123 inches in diameter, basically. Right? So our cable has to be either 0.123 inches or smaller. In our case, right, each strand, you see the diameter of each wire, is going to be 0.0612. So it's smaller. So we're good. We can choose this one as our high side cable. Let's do the same thing. You can see here I've highlighted it, but let's rationalize and understand why I chose that one, right? So for the low side, we need a larger conductor, okay, which sounds kind of weird, but the reason why is because the low voltage side, is going to have the high current. So we need a larger conductor so we have basically less resistance. So here we have 191,670 circular mil. Let's just zoom to this, okay? And we have here 167,800, but we don't have 191. The next highest one is this one, so we'll choose that one. 19 strands, and each strand is 0.1055. Remember that we need it to be less than 0.123, so we're good. We're less than it, we can choose this one. So those are going to be the conductors that we choose. All right, let's write that down. So this is going to be step 3. Let me see, did we write step 3? No, we should write it here. So step 3, okay, here we have to, from AWG table, pick a cable, size, that's equal to or slightly larger than what you calculated. Okay, so for the high side, so area circular mill for the high side, we chose the 26,240 circular mill. This one corresponded to AWG 6. AWG stands for American Wire Gauge, okay? That was the, you see, AWG 6. All right. Now let's go back. And we chose for the low side a circular mill. Let me just hold this up a bit. A circular mill low side. That one was going to be the 211,600 circular mill. And this corresponds to AWG 4/0. 4/0 is just the 4 zeros like this. Okay. All right. So, what we're going to do now is we actually have to consider insulation. So, to account for the insulation, right, these numbers are not including the insulation. This is the circular mill of the conductors, of just the conductor, no insulation, okay? So we're going to have to consider a little bit of insulation. Usually in the transformer, we're not going to have, like the cable I passed around the other day, that has a very thick, that white insulation, very thick insulation. This one is not going to have such a thick insulation. Usually it's going to have something called enamel. Okay, it almost looks like the wire is bare. It's not completely bare. It has this enamel that sort of prevents any short circuit currents. So we need to consider that. And there's another rule of thumb for that. Okay, so to account for insulation, use rule of thumb. Okay, so the actual physical, I'm going to call it PHY, the physical circular mill area, right, is going to be the one that we chose, but we're going to divide by 0.7. Okay, so that's going to turn out to be 37485.7 circular mil. Okay, just a little bit wider because of the insulation. And of course, we're going to do the same thing for the low side conductor as well. Where we have, this is the 211,600 C mil. We divide by 0.7, and the number becomes 302285.7 circular mil. Okay. Now remember that circular mill is a cross-sectional area. Okay? It's not a diameter. It's a cross-sectional area. So we need to find the diameter of the cable, okay, with this additional insulation factor. So to do that, we're going to use the formula that we discussed over here. Okay? In this formula, this 2 is kind of being blocked, okay? The area in circular mill will be equal to the diameter of the cable in inches squared times 10 to the 6. So we can basically just reverse this equation, solve for D, and find the diameter in inches. Okay, so we're going to do that with these cables now. So let's find the physical diameter. So D physical, which one did I do first? High side. All right, we got to take the area in circular mill, which in our case, let me use the same subscript. We got to divide by 10 to the 6 and then take the square root. Basically reversing that equation. So we're going to have this one was 3748.5.7 circular mil divided by 10 to the 6. And this, when you punch the numbers in, turns out to be 0.19 0.36 inches. That's going to be the physical diameter of the high side cable. This is a good number to put in a red box. All right, we're going to come back to that. And let me actually move this guy over here. All right, we're going to do the same thing now for the low side. Okay, exactly the same, except we just substitute the appropriate circular mill area. Okay, so we're going to have, the number was 302,285.7 circular mill. All right, this is going to be 0.5498 inches. Okay, that's the physical diameter of the cable with insulation included. Okay. We're going to need that physical diameter because we're going to need to find out how many turns, right, and how much space it's going to take on the actual core. That's going to be, in my opinion, that's the most challenging part of this assignment, is to find out how much space is required, okay, by the number of turns. Number of turns is easy to find, but basically, how do I arrange it such that it's not taking too much space, so the core is not too big? Okay, we're gonna get there. All right. So far, any questions on this? Okay. Number 4, step 4. Is to determine the number of turns. So it turns out there's an equation that relates the voltage to the number of turns and the flux and all that stuff. So the equation is given like this. It's 4.44 times number of turns times the frequency times the flux density, and finally times the cross-sectional area of the core. Okay. This basically comes from Faraday's law. Okay, that's basically where this comes from. All right. Now, we have to choose now the dimensions of the core. And also, we're going to have to choose basically what flux we're going to want to push through this core. So for example, okay, let's see here. We're going to get to this part in a moment, but the core is basically going to look something like this. Obviously, it's going to be 3D, right? So, you know, it has this portion. And we need to basically find out how thick is this core going to be, okay? For this example, I'm going to choose it to be 5 inches. In other words, if I were to take a slice here, right, I would find that it's going to be 5 inches by 5 inches. I'm just going to choose it to be that way, okay? If I take a slice of this guy, right, let's say I were to draw it over here, right, it would look something like this, okay? And I'm going to make it 5 inches by 5 inches. Okay. Oh, where are we? Here we are. Okay. So, choose core dimensions. 5 inches by 5 inches. And we're going to start with B equal to 1.35 Tesla. Okay, I'll explain in just a moment what I mean by that. Right now it might seem a little bit weird. I need to show you the graph and it will make sense. All these will close. look at a graph. Picture is worth 1,000 words. Let's go look at it. Okay. We're going to be looking at the black curve on this graph. And basically, this is the BH curve, the hysteresis curve. Okay, remember the hysteresis curve? That's what this is, this thing over here. It's just showing you the top right portion, basically. Okay. Here we have the magnetizing force, and here we have essentially the flux density, B. Okay. They put it in units of kilogausses. Okay. But it's an easy conversion to go from kilogauss to Tesla. 1 Tesla is just going to be your kilogauss divided by 10. So for example, if I have 13.5 kilogauss, that's the equivalent of 1.35 Tesla. You just divide by 10. And we're going to choose the flux density to be 1.35 Tesla. So that corresponds to 13.5 kilogauss. We go and see where that meets with the curve here, okay? And we see that it's in the portion just before the saturation region, right? Which is what we want. We don't want to saturate the core, okay? If we choose B to be like at around 18 maybe, or maybe a little bit lower, something like this, right? We're in the saturation region, and we're basically saturating the transformer. And what's going to happen is that your core losses, actually I should ask you, what's going to happen if we saturate the transformer? Anyone remember?
The hysteresis curve,
Right, it gets wider, right? And what does that mean?
right? It means that it has to put out more.
Basically, I see what you're trying to say. Basically, you're trying to say it has to work harder
Yeah.
than it should, right? Because you have to force the current to go the other way and all that stuff. So, long story short, what that means is that your core losses will get larger. Basically, the wider the curve is, the more your core losses are. And that's what we don't want, right? We don't want to do core losses to be too big, okay? So, let's stick around this point over here, okay, which is right below the saturation region. Basically, saturation region is somewhere over here. This region is like the knee, and then here it's starting to go into the saturation. Okay, so as long as you're around or below the knee, you're fine. So we're going to choose B equal to 1.35 Tesla. All right. So from the core dimensions, okay, we can find that the cross-sectional area of the core, right, is going to be 25 inches squared. I mean, it's pretty straightforward, right? 5 times 5, 25. Okay? Now, we're going to convert area of the core, right? It's 25 inches, but we're going to convert it into meters squared, because that's the equation is designed for meters squared. So if you convert it to meters squared, it's going to end up being 0.016129 meters squared. Okay? And what we're going to do now is find out how many turns we need on either side to get whatever voltage we want with these parameters. So for example, if I solve for n, right, I'm going to get the following. If I solve for n, I'm going to have V over 4.44 times F times B times area of the core. Now, if I want the number of turns on the high side, I need to input the voltage on the high side. Okay? That should be an S, not a phi. All right? So voltage on the high side was supposed to be 6,600 volts. Frequency is going to be 60 hertz. All right. B, we set it to be 1.35 Tesla. And area of the core, we got to put it in meters squared, so it's 0.016129 meters squared. And we find from here how many turns we need for the high side. When you punch the numbers, you should get 1138 turns. Okay. Let me pause here for any questions. Make sure everyone's with me here. Okay. Through a similar, basically the same thing except for low side, we're going to put the low side voltage. So number of turns on the low side, right? It's the same equation, but we now have to put voltage on the low side, okay? In fact, I can just do it like this. In other words, I'll just, so that's, when you're doing it yourself, it's a little bit more straightforward. This is for low side. Okay. V low side was supposed to be, I think it was 600 volts. Again, 60 hertz. We have 1.35 Tesla. And the cross-sectional area of the core is still 0.016129 meters squared. So number of turns on the low side is going to turn out to be something like 104 turns. Okay. Okay. So, I'll give you a moment to write. So, from the number of turns and the diameters, we'll be able to find out how big the core has to be. In other words, how tall does it have to be? How wide is it going to have to be? All that stuff we need to find out using this set of information. This part, in my opinion, is not, the part that we're about to do is not the most straightforward thing, so make sure you're paying attention because I want you to make sure that you understand it when you do it yourself, okay? In my opinion, the hardest part is coming up right now. It's not, I wouldn't say it's crazy hard, it's just you have to follow it, okay? And then you have to understand it. Okay, so I'm going to turn next page. All right. So basically, the transformer core is going to look like this, where essentially you're going to wrap the turns like this. This is going to be, let's say, your primary winding, okay, and you're literally going to wrap the secondary winding right on top of it. Okay, we're not going to do it the way that we teach it. In other words, we teach transformer is like this, right? But in reality, that's not going to work because it's impractical. We lose a lot of leakage, right? So it's much more efficient to put the turns right on top of each other, and that's what we're going to do. Okay. Now, as you saw, we have a lot of turns that we have to do. Okay. So we need to make sure that when we're done wrapping all the turns on top of each other, that this space, which is called the window, we want to make sure that the window is not completely blocked. Okay? We want to make sure that the window has a little bit of space. Ideally, we want to take up only 75% of the window. So in other words, we want to maybe take up this much and leave the other portion empty so that we have some room for ventilation. Okay? So I'm going to zoom in on this portion, which I have over here, okay? And we're going to start basically figuring out how we're going to do the turns on this transformer. Let's start with the low side cable. And the reason I want to start with the low side cable is because it's the bigger of the two. Okay. I'm going to draw the low side cable, by the way. I'm going to draw it in blue. Okay. So basically, we're going to wrap the turns like this. All right. You can imagine, right, this is going like this, right? And then we're going to wrap the next layer. Okay. Now, as a reminder, the diameter of the low side cable, I remember the number because I did this before, right? If you don't remember, you have to flip back. But basically, the diameter should be 0.549 inches. Okay? So let's see how tall the transformer has to be just so that we can wrap only, let's say, one layer. This would be considered one layer, right? Like this. Okay? So basically, we need 104 turns, and each of them, right, each turn is going to be 0.5498 inches tall. So basically, we're going to do 104 times that. So let's do it. It's going to be, here's the calculator, it's 104 times 0.5498. So that means that we have to have a 57-inch tall transformer. If that sounds big to you, then you're thinking correctly. It's too big, right? That's very tall. It's like what, like 5 feet? Almost 5 feet. Okay. It's tall. It's too big. Okay. No one wants to use a 5 foot tall transformer. Okay. So we want to actually try to make it shorter. And the way that we would do that is we actually would layer. In other words, let me explain. This is considered one layer. Let's say I wrap it like this, okay? But what if I do another layer like this on top of the first one? Okay. So in other words, let me finish this, okay? Okay, I wrap it once, and I wrap on top of it again. Okay, that basically gets me more turns without taking up too much vertical space. Okay, because if I just do one layer, the vertical space I need is 57 inches. That's huge, right? So I can double the layer, and then that'll help me shorten the height that I need. Okay? So for the sake of time, I'll just tell you that it's best to do about 4 layers. Okay, 4 layers. Let's do it like this. Let me go like this. Okay. And I'll show you mathematically that this is it's going to work. Okay? And let's say again that we do all the way to the bottom. I'm not going to draw every single one, but let's go like this, okay? Something like this. Okay? Dot, 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 okay? If we take 104, that's the total number of turns we need, and we divide it into 4 layers, that means we only require 26 turns in height, basically, vertical turns. So we have to basically distinguish between vertical turns and layers, right? So with 4 layers, if we do 4 layers, we're going to need 26 vertical turns to complete all 104 layers. Okay, turns. So if I do, because it's 26 in the height, in the vertical, if I do 26 and I multiply by the diameter of the cable, I find that this will take about 14.3 inches. Okay, so it's about like a foot and a little bit, something like this. Okay, which is a lot better than from, 5 feet tall, right? So let's note that. Okay. If we use 4 layers, we'll need 26 let me put it vertical turns. Okay. This will take up 14.3 inches. Okay. So exactly 14.3 inches to do 4 layers on our transformer. Now, we don't want a snug fit. So we're going to basically give a little bit of wiggle room on the top and on the bottom. About ½ an inch, top and bottom, is decent wiggle room. Okay? So give 0.5 inch wiggle room on top and bottom. So basically we end up with a total of 15.3 inches in height. Okay. So from here to here, okay, the total is going to have to be 15.3 inches. Okay, including the wiggle room. All right, that's going to be that height. All right. Questions so far? Okay. Now, let's let me do this first. So before I put this, let's do this. This blue arrow is going to represent the height of the low side turns. So it's 14.3 inches without the wiggle room. Okay. 26 vertical turns. Okay. Now we're going to have to put the high side turns on top of this. Okay. So we're going to have to put the high side turns on top of it. Now, we are, in a way, already committed to the height. We've committed already to the height. Okay. So we have to sort of work with that height. Okay. So I'm saying with the 14.3 inches because I still want the wiggle room even after I'm done with the high side turns. Does that make sense? Okay, that's why I'm working with 14.3, so that I still have wiggle room at the end. Okay, so now the diameter of the high side conductor is going to be 0.1936 inches. Okay, we calculated it. Okay, so we need to see basically how many turns we're going to get vertically. All right? Anyone know how we can do that?
Divide the 14.3 by that.
Yes, very good. You take the 14.3 and divide by that diameter. So it's 14.3 divided by the diameter of each of those cables. All right, which is 0.1936. All right. So we're going to require roughly 74 vertical turns for the same height. Okay. So for the same height, we'll need 74 vertical turns for high side conductor. Okay. So we're only going to fit on one layer 74 turns vertically. Okay. However, we need something like 1,138 turns, right? So we're only going to take care of 74. How many layers do we need? How can we do it? Find how many layers we need?
Divide those turns by 74.
Right, you take the 1138 and divide by 74 to find out how many layers. Okay, so we take 1138, divide by 74, and we need roughly 15.4 layers. 15.4, right? 0.4, all that means is that the last layer will not be a complete turn, which is fine. Okay, we can live with that. So to complete 1138 turns, we'll need 15.4 layers. Okay? I'm not going to draw every single layer, but you get the idea that they're going to be 15.4 turns. 15.4 layers. Okay? Okay. Now, this is it's getting kind of thick, right? We need to find out, right? We want to make sure that the window is wide enough. We want to design the window so that this will only take up 75% of the window. All right? So we care mainly about this length, which is from all these conductors and then all the 15 conductors. So we can calculate the width, all right? We don't care about outside the window. In other words, we don't care about these guys. We only care about this width. So the width, right, that this is going to take up, we have 4 layers of the 0.5498 inch conductor. And then in addition, we're going to have 15.4 layers of the smaller conductor. Okay, so in total, this is going to take about 5.18 inches. Okay, so now we can calculate, and we're going to take a break after this. We're going to calculate the width of the window. Anyone want to take a guess how we can ensure that it only takes... Let me go like this. Core window width. Okay. Basically, what you have to do is you take how big this is going to be and divide by 0.75. And this will give you 6.9 inches, which is basically, just make it 7 inches, because it's better to be a little bit big, right? So if I make my window 7 inches wide, my turns will only occupy 75% of that window. Okay? So this is going to be the design parameter we're going to need for the window, 7 inches wide. Okay? All right, let's take a break, take about a 10-minute break. Okay? We'll move to the other room, and we'll resume after that. Okay? All right? So, we found out how wide the window has to be. All right? Now, the challenging part is to find essentially how long the wire has to be. Okay, that's going to be the challenging part. Let's look at just 2 turns, and from there we'll extrapolate, and I'll show you a quick way to do it, so you don't have to waste too much time doing it. All right? So, imagine that we slice the core, right, like that. Take a slice, and look at it from the top. In other words, you slice here, look from the top. If you were to do that, you would get the following. You would have a something that looks like this. Maybe make it thicker. Something like this. All right? We're looking at it from the top. Okay? And when we wrap the turns, right, we're going to wrap them around like this, right, in this direction. All right? Let's start with the low side because it's fewer layers. Okay? And let's say that we have one layer like this. Okay? And let's say now that we want to find the length of that layer. Okay, let me just, I want to make this exact, or as close to exact as possible, because then everything will be very clear. So let's go like this. I want to get it right on the line. Yeah, that's good. Okay. So, okay. To find and imagine this is the wire. Basically, this whole thick thing is the wire. Okay? If you want to know how long that length is, what we're going to do basically is we're going to look at this distance, the center distance, also known as the mean length. Okay? The mean length. So the length, basically the length of this entire thick wire, right, we can find it essentially by finding just this distance, okay? So, let's rationalize, let's think now. The width of the core, this part, how much did we say it was going to be? 5 inches, right? This one is going to be 5 inches, right? So the width is 5, and so is this, okay? 5 inches. All right? Now, it's not exact, but this distance, right, should be equal to what? Diameter, very good. It's the diameter of the cable, okay? So, if I consider, right, this is going to be half a diameter, okay? And this will be also half a diameter. Bless you. So basically, this entire distance here, from here to here, which is equivalent to the distance from here to here, right, is going to be 5 inches plus half a diameter plus half a diameter, which becomes just 1 diameter, right? Okay? Now, I have, how many of those distances? I have 4 of them, right? So it's going to just be 4 times whatever that number is. So let's write that down. Length of, and I use a capital script L, length of one layer is going to be 5 inches plus diameter of low side divided by 2. I'm writing it like this on purpose, by the way. So divided by 2 plus diameter of low side divided by 2 Okay, and then the whole thing I got to multiply by 4. All right? That's going to be the length of one layer. Let's do another layer. I'm going to draw the second layer in red. What I'm showing is that it's basically the same cable. You know what? Let me not use red so that you don't get confused with the high side cable. I'll use like a pink, okay? So, let me move this lower, like here, okay? Let's do the second layer like this. Okay? So, assume it's the same conductor, which it is the same conductor. I just drew it a different color so you can see it better. So we're going to now calculate the length of 2 layers. Okay, so first of all, the length of 2 layers is first we need to do the length of the first layer, which we have already. Okay. Plus, now we got to do the length of the second layer. So again, we're going to need to find the mean length distance of this pink layer. Okay? And we're going to do the same procedure, right? We have this width of the core itself is 5 inches. Then we have to consider this distance, right? So that distance is going to be what? If this distance is a diameter, then what is this distance?
Diameter and radius.
Exactly, diameter and a half. Okay? 1.5 diameters. So, we're going to have 5 inches plus 1 diameter and a half, and on the other side also we're going to have a diameter and a half. Right? And that's going to account for this entire distance, which is the same as this distance. And because it's a square, it's the same as this distance, and the same as this distance, and so on. So you got to multiply by 4. All right? This is going to simplify, don't worry. So we don't have to do this for 15-something layers, right? Okay. So when you work this out, just sort of open up parentheses and combine everything, you're going to find that this is going to be equal to 4 times 10 inches plus 2 diameter plus 2 diameter. Take out a 2 common factor and notice something. So here, if you take a 2 common factor, the 10 inches becomes 5 inches, and the 2's over here become just 1's. Okay? Let's see what this represents. 5 inches is this distance, and 1 diameter is exactly here on either side, right? So in other words, this is 1 diameter, and this is 1 diameter. So this distance is actually giving me this whole thing. Okay? And you're multiplying by 4. So basically this part over here that I'm circling in red is going to be this distance in the thick blue line. The thick blue line is the midpoint between the both layers. It's the midpoint of both layers. Okay? So in other words, to find the length of 2 layers, pay attention, to find the length of 2 layers, you need to find first the length of the midpoint between the 2 layers, okay, which is the 4 times this whole thing. And then you got to multiply by 2 because there are 2 layers. Okay? So let's make a note of that. 2 is corresponding to the number of layers, right? And the whole rest of it is just finding that midpoint, or exactly that midpoint between the 2. Okay? So now what we're going to do the same thing, but we're going to do it for the low side conductor. In the case of the low side conductor, we have 4 layers. So what's the midpoint? Exactly. In other words, we need to find this distance is going to be the 5 inches, right? This is 5 inches. And then the midpoint is going to be up to here on either side. Okay? So let's write. The length of the total low side conductor, leave some space. It's going to be 4 times, right? We have the 5 inches plus 2 diameters, right? Plus 2 diameters. That's going to be this distance over here, right? This is the midpoint, okay? We multiply by 4 because we have 4 sides. And we have how many layers? 4, so we're going to multiply by 4. Okay? Now, let's do it like this. Multiply by 4. Now, this takes care only of one vertical layer. In other words, it takes care of only this step. So we have to multiply by what? 26, right? Because there are 26 of them. We just did one step over here, right? We basically found the length of this portion. But we need to find the length of every single portion. So we're just going to multiply by 26 because they're all the same. There are 26 vertical layers. Okay? So multiply by 26. So this 4 is how many layers? And this number is, you can think of it as vertical layers. Or you can think of it as turns. Let's call it vertical layers. It's better that way. Vertical layers. Okay. Now notice, what's 26 times 4? 104, which is exactly how many turns you need, right? Multiplied by, and then of course you have the 4 here. Let's do like this. Times this thing. Okay? So, what's the moral of the story? Is this,
Blurry at the bottom.
it looks blurry
Yeah.
from my distance. Is it blurry for you guys?
Yes.
Give me a moment to fix it. I was wondering why you guys are not seeing it. It's blurry. There you go. I was wondering if my contact lenses were like, something was wrong with them. Okay. So, how do we do it again? Let's review. This, okay, in the square brackets corresponds to the midpoint length. Okay, the midpoint length. It's going to be the 5 inches here plus 2 diameters on this side plus 2 diameters on this side. Now, you have 4 of them, right? Because it's a square core. So you multiply by 4 to account for the square, right? You have 1, 2, 3, 4, right? You multiply by 4. And then finally, you multiply by how many overall turns you need, which in this case is 104. Let me pause here. Any questions or confusion about this? In my opinion, this is the hardest part. Okay? Okay. Let's crunch the numbers. If you were to crunch the numbers, you'll find that this gives a length of 2994.87 inches. Now we're going to ultimately want this in feet. So I'm going to ask you guys, how do we convert to feet? Everyone should know this. Divide by 12. Very good. 249. So when you divide by 12, you get 249.57 feet. And that's going to be something that you're going to want to box in red. We're going to return to that. We need the entire length of that cable because we need to find the resistance. If we find the resistance, we can ultimately find the copper losses. Okay, that's what we need to find, because at the end we need the efficiency to be over 99%, right? So we need to find the length. That's why we're doing this. I'm not doing this just to, torture you. I'm doing this because we need to find the losses ultimately. Okay. Okay. Now, for the high side, but it's going to be easier now because we know how to do this. Okay? Let's think how we can find the length of the high side. Okay, so length of the high side. We're going to do it. I know that we can do it. So, now, initially, right, we were just starting with this length. The 5 inches was constant. That was not changing. Okay? But now, we are wrapping the high side on top of the already completed low side. So now, the length that stays constant is no longer 5 inches. It's going to be 5 inches plus what? This is the 5 inches. What are we adding to that?
8 DLS plus 8 DLS.
Right, 8 diameters, right? Because we have to add this many diameters, which is 4 diameters, plus another 4. This is the distance that's no longer changing, right? This is the constant distance. So instead of doing 5 inches, it's going to be 5 inches plus 8 diameters of the low side conductor. Following or no following? Okay, cool. So that's going to be the sort of the constant number. All right. Okay, so let's do it like this. We have here the 5 inches plus 8 of the low side diameters, which is 0.5498 inches. Okay. Now to that, we have to add, right, basically to find the midpoint, right? To find the midpoint from here to wherever that midpoint is. Now we have 15.4 layers. So the midpoint for 15.4
8.6.
7.7, but yes. Okay? It was pretty much correct, yes. 7.7, okay? So we're going to add 7.7, right, of the high side diameter. So it's the physical high side, 7.7 high side. All right. That's going to be that entire midpoint length. Now, we got to multiply by 4, right? Because we have 4 sides. And then we multiply by what?
15.4 and 74.
Right, which is going to give you 1138. Excellent, very good. I'll put it like this first, and then I will put it like this. Okay? Okay? So basically the procedure is you need to first find that midpoint, or rather, first you need to find that constant length that's going to stay constant all the time. Then you find the midpoint, multiply by 4 because you got 4 sides, and then multiply by number of turns. Okay? So your high side length, when you punch it out, becomes 432.26 inches. And you're going to want to convert that into feet. So in feet, that becomes 4,702 feet. Okay? You guys got to, okay. This will be online probably by tonight, if not tomorrow. Okay? All right? All right. So now we're ready to calculate the resistance of those conductors. Okay? How are we doing so far? It's a lot of number crunching. I know it is. Okay? All right. Now, to find resistance, anyone remember the equation for resistance? It's been a while. I know. It's been a while. I'll give it to you. It's rho L over A. Rho L over A. Okay? This, you guys probably covered this a while, an intro to electrical. How long ago was that? 2 years?
2 years on the try, yeah.
Yeah, that's a while ago, okay? So if you forgot it, don't worry, all right? I remember this because I do it all the time. That's why I remember this, okay? But if I were in your shoes, I would have also forgotten after 2 years, all right? Don't feel bad. So, L, in this case, is the length of the conductor, which is what we just found for both high side and low side. A is going to correspond to the circular mill area, cross-sectional area, and rho is something called resistivity, okay? And that's unique to the material. Every material has a unique resistivity. I'm going to give you the one for copper because that's what we're working with. So resistivity of copper is going to be 10.371 circular mill. Let's do it like this. Ohm times circular mill divided by feet. Okay? That's the units. And you'll see that it works out very well with the equation to give you ohms. Okay? All right. So, let's do this. Let's do our low side first, our low side. Okay? The rho is going to be 10 point, we have it already, it's a constant. We're going to multiply by the length of the low side conductor, which we had on the previous page, was 249.57 feet. And we're going to divide now by the cross-sectional area in circular mill. Now we're going to use the 211/600 circular mill. If you are sort of watching very carefully the numbers, and it's okay if you aren't, but when you look at this later, look at the numbers. This 211/600 circular mill is the cross-sectional area of the conductor without the added insulation. Okay, let's go back to show you that. Right? This one is the circular mill for the low side, but without, okay, no added insulation. Why we don't add the insulation? Because to find the resistance of the copper, right, the copper is the one that's going to have current running through it. Okay, we need to know the resistance of the copper. Therefore, we need the length of the copper. Okay, so we don't need insulation there. We just want the circular mill area of the copper only. Okay? So, you punch the numbers and you're going to find that the overall resistance is going to be 0.01223 ohms. We do the same thing for the high side. Okay, length of the high side is 4702.69 feet, and the circular mill is 26240 circular mill. This becomes 1.859 ohms. Okay? Questions so far on this? Okay. Now we can easily find copper loss. Okay? So P copper, let's do low side first. Basically, to find the copper loss, how do we do it? I know you guys know this.
B squared over
You could do V squared over R. Traditionally, it's done
R, I squared.
I squared R. Yeah, traditionally it's done I squared R. But you could do it, in this case, you could do V squared over R. Okay? So I'm going to do, I have it here, I have the number written down here, I squared R. So what we're going to do, though, you have to be careful, okay? The current that we're using is we're going to use the rated current. Not the 15% over. Remember we calculated 15% over? Don't use that current. Use the actual rated current. Okay? Because we want to find the losses for normal operation, not for over operation. Okay? So, we take the current, and let me actually maybe write it like this first. So we put here I rated low side times R low side. Okay, and if you want, you could do it V squared over R and check that you get the same answer. You should get exactly the same answer. Here we get 166.67 amps squared times the resistance, 0.01223 ohm. And this becomes 339.74 watts. Do the same thing for the high side. Okay. These are the numbers. And to find the total copper loss, as you can probably guess, you just add them together. And you'll find that your total copper loss should be 766.4 watts. Okay. Almost there. Almost there. Okay. We need to find the core losses now. All right? And that part is not as bad as this. This was the worst part. Okay, so it only gets better from here. Okay. So, core losses is going to involve us having to find the volume of the core. This is why we needed to get all those dimensions. Okay? So, including wiggle room, right? This height from here to here, including the wiggle room, was supposed to be 15.3 inches. Okay? This width here is 5 inches. And ultimately, we'll see that this distance from here to here is also 5 inches. The window was supposed to be 7 inches. Okay? So, overall, this height, right, is going to be 15.3 inches plus 5 inches, plus 5 inches, right? Because you have the other distance up here. Okay. This distance from here to, okay, is going to be 7 inches plus 5 inches plus 5 inches. Okay? To find the volume of the core, in my opinion, the best way to do it is to find the volume of a big chunk like this, and then cut out the volume of the little chunk. Okay? So, volume is going to be volume of the big guy minus volume of the little guy. All right? Volume of the big guy. We need the height, the width, and the depth. In our case, the depth will also be 5 inches. All right? So, this distance, 7 plus 5 plus 5, obviously 17 inches. Okay? This height over here is going to be 25.3 inches. And finally, we multiply by 5-inch depth. Now, the little guy, which is the hole, the donut hole over here, okay, is going to be 7 inches, all right, plus, times 15.3 times 5-inch depth. Okay? Punch these in, and you get that the volume is 1615 inches cubed. Okay? Now we're going to have to go through a series of conversions. I want to convert it first. Into centimeters cubed. So 1 inch, how many centimeters?
2.5.
Very good. Very good. Very good. So to convert it, right, let's put a little arrow. Okay, when you convert it, you should get that this will be, the volume is 26465.1 centimeters cubed. Okay? From here, we can find the mass of the core. And we use basically this conversion. 7.65 grams per centimeter cubed. Okay? So, core mass is going to be 26,465.1 centimeter cubed times the conversion factor, 7.65 gram per centimeter cubed. All right, and you're going to find out that this is going to be 202,458.079 grams. Okay. We need this because the chart that we're going to use requires us to have, actually we're going to have it in pounds. We need to convert this into pounds. Anyone remember? 1 gram is how many pounds? You're there. You're almost there. It's 2. Right. Roughly 2.2. It's 2.2, I think, 04 or something. I don't remember exactly, but 2.2 is sufficient. Okay. Good. Good. Make sure that you guys remember this. All right. 1 kilogram. Yep. Very good. So we convert. Oh, I forgot to convert it into kilogram. That's easy conversion, though. Anyone, you guys, I know all of you can do that with no problem. I'll just write it down. Okay. That's going to be 202.079 0.458. All right. So convert to pounds. Okay. So the core mass is going to be 445.408 pounds. Okay? That's heavy. All right. Now, we need to know the core losses. Luckily, we have a table that will give us the core losses. Not a table, it's a graph, but still. Makes this a lot easier. All right? And I've given you that in here. Okay? So again, on the left, or rather on the y-axis, we're going to have the Teslas. And on the x-axis, we're going to find the core loss in units of watts per pound. So basically, I have my pounds, multiplied by watts per pound, I find my core loss in watts. Okay? Now the Teslas that I decided to have 1.35. So B is supposed to be 1.35 Tesla. Now, of course, this graph gives it to you in kilogauss, right? So basically, in kilogauss, it's 13.5 kilogauss. Okay? So we're going to have to see where the 13.5 kilogauss crosses with the 60 hertz cycle. We're here in North America, right? We're not deciding for Europe. So we'll see where that crosses. And it crosses to 0.4 watts per pound. Okay? So from here, we'll be able to find exactly how many watts we're going to lose in core losses. Okay? Okay. So, oops. So, according to graph, at 1.35 Tesla, the core loss is 0.4 watt per pound. Okay, so P core, all right, we take the pounds, which is 445 point, very good, thank you, and multiply by 0.4 watts per pound. And we get 178.2 watts. All right, we're in the home stretch. Okay. Last thing is to find the efficiency. Okay? Remember, the efficiency must be 99.1 maybe, or 0.01. As long as it's above 99, you're good. So the last step is to find efficiency. So finally, okay, efficiency is going to be P out over P out plus P copper plus P core. Now, we're going to assume, because we need to find P out, right? To find P out, we need to assume power factor. And we're going to assume power factor equal to 1. Okay, unity power factor. Okay, so P out is going to be the S that we decided on times the power factor, which in our case should end up being 100,000 watts, right? Because our S was 100,000 volt ampere times 1, obviously 100,000 watts. Okay? And now we just plug in our numbers that we calculated very carefully. Okay, the copper losses were 766.4 watts. And right now the core loss was 178.2 watts. And you should get 0.9906. Just made it. But it still counts. It's good. Okay. Now, let's say that you get 98%. Okay, not a big deal. What you have to do is you take the B, which was 1.35, and jack it up a little bit, make it 1.4. And then repeat whatever you have to change. Okay? And then you should get it to work. Okay. Now, this might seem daunting, so I'll give you sort of a guideline. I want you to do different numbers, but what I'm going to give you a guideline is, why don't you try S equal to 175 kVA and keep the same voltage. And you don't have to use these numbers. You can use different numbers if you want. This is just a suggestion if you want to try it. I haven't done this, so I'm not sure. Or maybe I did this, but I did it 2 years ago, so it's like I never did it. I don't remember. Okay? So I recommend trying this one. It should work out if you follow the same procedures. Numbers will be a little bit different. Okay? Any questions so far on this? Okay. There won't be homework this week. I'm just going to let you do the design project. I recommend, this is a long thing. Don't do it last minute. Okay? Take at least a day or two to do this. Yes?
Yes, and when is this going to be due?
A week from tomorrow. I'll give you a week. Okay. If you guys think you need more time, let me know. All right? I think a week should be fine, but if you need more time, let me know. All right? For the design project. Okay. Now, this class, so let me end the